Thank you for joining us today in our webinar on 6 things to consider when choosing a wireless module. At the end of the session, I hope you'll come away with a better understanding of device-level considerations, time to market, and compliance for RF and wireless modules. This session is geared towards providing an overview of the following: key market trends, key wireless module criteria such as power, frequency, modulation quality, key design tests, be it regulatory or protocol, pre-compliance in EMI considerations, situational field RF testing, and lastly, product features and their test and measurement functionality. Let's begin with a brief market overview. To better understand why we're here today, and in terms of the wireless Internet of Things technology, you can see the massive growth projections of the number of smart devices that we'll have by year 2020. The graph above depicts that there will be approximately 3 times the number of connected devices than there will be humans by year 2020. With this explosion of the Internet of Things and all things wireless, there will also be a quote-unquote interference of things, and it will be becoming increasingly critical to ensure that these wireless devices are operating as expected. Add to this is the complexity of taking megatrends into consideration of the Internet of Things. The below slide provides another proof point of how fragmented the overall industry is from the wide range of services, sectors, and segments, as well as applications and ultimately devices. The variety of these market segments and the related applications addressed by these wireless Internet of Things devices and the speeds at which these will continue to grow all make it all the more imperative that a designer of wireless Internet of Things devices test devices quickly and accurately in order to meet time-to-market considerations. This slide summarizes what is driving this huge growth in wireless Internet of Things devices, specifically in the integration of several chips onto a single module. Through the end of 2016, we now see the average costs being driven down on an accelerated basis. And based on the ability to modularize a wireless Internet of Things solutions onto a single carrier or module. This not only brings in a variety of test requirements for a single package, but also brings engineers over from one area of expertise into new areas of testing. That is to say, a firmware engineer for a microprocessor might actually have to check RF tests to ensure that the on-chip transmitter is emanating signals as expected. Let's now move into the wireless module selection. In order to properly choose the wireless module for your subsystem and application, you need to first understand the wireless standards you will be working within. There are 3 key factors to consider when evaluating wireless technologies: coverage range, data rate, and power requirements. The figure on this slide shows the major wireless standards divided into 3 range categories. The vertical scale presents the difference of transmission speed or data rate. As you go along the vertical axis, data rates increase, and as you go along the horizontal axis, range increases. The coverage range of a wireless network is limited by technology, transmission power, antenna type, geographic location, as well as the environment. Based on the network range, wireless connectivity standards can be categorized into 3 large classes: wireless wide area network, wireless local area network, and wireless personal area network. Over the next several slides, we'll be looking at some of the key standards and the considerations within. Any wireless or IoT application that requires operations over very long distances can take advantage of cellular communication capabilities. Traditionally, those cellular standards are dedicated to voice and data communication with long-range coverages of tens of kilometers, as highlighted in the table From the beginning of cellular standard development, many technologies have been adopted and continue to be used today, such as, for example, wideband CDMA. Conversely, LTE and the next generation of 5G is becoming the mainstay of cellular coverage, providing circa 100 megabits per second data rates across up to 20 megahertz of bandwidth. The concept of wireless LAN was initially introduced to provide the quote-unquote last 100 meters of connectivity, which refers to the low-power wireless devices that operate in a very short range of 100 meters. The wireless LAN communication standards use license-free frequency bands, mainly 2.4 gigahertz or 5 gigahertz. Thus, wireless LAN standards offer free-of-charge connectivity services. Protocol compliance for the Wi-Fi standards is managed through the Wi-Fi Alliance. This alliance, which is an industry group whose mandates are to ensure that devices with a Wi-Fi interface A, conform to specific performance levels for interoperability, and B, security. Specific information on membership, certification test houses can be found on the Wi-Fi Alliance website shown here on this slide. Wireless Personal Area Networks, or WiPAN, usually cover a shorter range than that of wireless LAN systems. It also has a lower data rate, lower power consumption, and typically runs on small batteries. WiPAN is widely used to transmit a small amount of data amongst devices such as computers, telephones, tablets, and personal digital assistants over a short distance. A common WiPAN application is a smartphone connected over Bluetooth to a handful of accessories such as your wireless headset, watch, or fitness device. The classic Bluetooth protocol is not so much encouraged for longer duration applications due to power consumption limitations. For smaller gadgets which run on batteries or limited power sources, new wireless technologies were needed. To fulfill these requirements, longer range WiPAN, a subcategory of WiPAN, was introduced and optimized for low rate data transmission, low power consumption, and often mesh network architectures. The IEEE 802.15.4 standard is the most well-known, which defines operation of long-range WiPAN. It specifies the physical layer and the media access controls over the long-range WiPAN. There are other 802.15.4 base protocols, including Thread, 6LoW WiPAN, RF4CE, as well as WiMi, summarize the major IoT wireless technologies for the low power and low rate transmission applications. The most widely deployed enhancement to 802.15.4 standards is Zigbee, which is the standard of the Zigbee Alliance. With this trend, Bluetooth was also introduced, a new lower power version of the Bluetooth standard protocol called Bluetooth Low Energy, or BLE, or some others have called it Bluetooth Smart. These are aimed at emerging applications in healthcare, fitness, distress beacons, security, as well as home entertainment industries. Similar to Bluetooth, Wireless LAN has also added their own version of 802.11ah to address these lower power markets. LoRa is a fast emerging and becoming a widely used protocol for low-rate wireless personal area network communication. LoRa presents the physical layer of long-range wireless communication created by the LoRa Alliance. This technology is designed to enable a gateway or base station to cover entire cities or hundreds of square kilometers. The most well-known application today using LoRa is smart metering. LoRa uses a spread spectrum modulation scheme with linear frequency modulated pulses, or LFM, or it's called chirp spread spectrum modulation, or CSS. This technology trades the transmission data rates with the receiver's sensitivity within a fixed channel's bandwidth. The variety of bandwidths are available from 7.8 kilohertz up to 500 kilohertz. Let's now move to certification of a wireless module. This slide is designed to talk about the types of certification and the differences between standards and regulatory requirements. Standard certification ensures that products can interoperate within the ecosystems and where they're deployed. New products will need to meet qualifications as defined by the standard selected. Regulatory certification or compliance, on the other hand, are subject to local geographic regulations. These regulations allow the products to be sold in a particular country. Wireless protocols or standards are needed to ensure that products can interoperate within the ecosystems and where they're deployed. However, to adhere to the standards in question, new products will need to meet the qualifications as defined by the standard selected. In other words, the products will operate within its standard means. It will not operate out of frequency channels or other designations for that standard. Qualification here is the term used to describe what tests a product is required to pass so it will meet a wireless standards. These said qualifications provide assurance that the product will interoperate with other devices using that same wireless standards. Failing qualification can mean design turns that will delay the final product release and draw additional significant development costs. The table within shows the most common tests for RF transmission as well as receive. For example, Wi-Fi certification as per the Wi-Fi Alliance. So in order to use the Wi-Fi certified logo on that product, firms must first become members of the Wi-Fi Alliance. As a member, one would submit their products for testing at a Wi-Fi Alliance designated certification house. And thirdly, the tests ensure that products meet specifications as defined by the IEEE 802.11 standards. To perform the tests in Step 3, the radio is put in direct transmission mode and run in different 802.11 modes and emitting channels. At the physical layer level, the radio output power is measured and other measurements such as specified emission shape and error vector measurements are also performed. Tektronix RF test products include a combination of hardware and software platforms. Specifically, the RSA 306B and the RSA 600A series USB spectrum analyzer offer high bandwidth laboratory spectrum analysis in a small, very portable package. They are ideal for testing wireless LAN, as well as other wireless technologies which we'll cover throughout this webinar. In this attached slide, you'll find tests being done on a Tektronix RSA 306B spectrum analyzer and using what we call SignalView PC software, which makes sophisticated wireless LAN measurements easy. On the 802.11ac, which is a 20 megahertz bandwidth signal shown, the spectrogram shows the initial plot sequence followed by the main signal burst. The modulation is then automatically detected as 64 QAM for the package and displayed as a constellation. The data summary indicates an EVM of minus 37.02 dB RMS, and the burst power is measured at minus 17.32 dBm. The SignalView PC applications are available on 802.11a, b, j, g, p, and including AC, which is a 40 megahertz bandwidth application. Also on a Tektronix RSA 306B spectrum analyzer using SignalView PC software, you can perform Bluetooth SIG standard-based transmitter RF measurements in the time, frequency, and modulation domains. This application supports basic rate and low energy transmitter measurements defined by Bluetooth SIG test specifications RF.TS.4.1.1 for basic rates, and then RF-PHY.TS.4.1.1 for Bluetooth's low energy standards. LoRa is essentially operating in the sub 1 GHz frequency range, depending on geography, and leverages scalable bandwidths. In the attached figure, the frequency versus time display in SignalView PC shows how the signal frequency varies with time. The packets are comprised of chirp spread spectrum segments, which can easily be measured with the RSA spectrum analyzer. Some other requirements are not specified by the wireless standards and are only subject to local geographic regulations. Operation in countries within defined regulatory domains may be subject to additional regulations. Implementers need to refer to the country regulatory sources for further information. Regulatory certification allows the product to be sold in a particular country because it meets the country's regulatory rules. Regulatory certification is to be obtained in a test house that has been selected by the local authorities. Regulatory bodies such as the FCC in the USA, Industry Canada or IC, and Europe has the European Telecommunications Standards Institute. The certification rules are twofold. First, there are general admission testing rules that nearly every electronic device must pass. Secondly, intentional radiation testing rules that only products designed to transmit data wirelessly must comply with. The rules may vary within a country depending on the frequency range and the type of intentional emission. For example, does the product have radio hopping or not? The rules may differ from country to country as well. Going through the regulatory emissions tests can range up to $15,000 per country in a test house, assuming you pass the first time. Compliance testing is exhaustive and time-consuming, and a failure at this stage of the product development can cause expensive redesign and product introduction delays. Pre-compliance testing is intended to assure that the product has a high probability of passing the compliance test. And the goal is to uncover potential problems and reduce the risk of failure at that compliance test stage. Let's now cover EMI pre-compliance for your wireless module selection. In the United States, designers have reported spending about $10,000 for one visit to do external compliance testing. At the same time, designers have also reported that less than 10% of the time do they pass their first try for compliance testing. So in short, EMI testing is very expensive. Multiple visits to a test house can add significant cost and delay to product launch. Performing basic pre-compliance testing in-house beforehand can help minimize product development time and can minimize expenses by catching out-of-specification conditions before the device is sent for formal compliance testing. When it comes to EMI characterization, we basically have two perspectives. One is compliance, the other is pre-compliance. Compliance measurement involves a large capital outlay, not only for the equipment, but also for the physical setup. To build an anechoic chamber of anywhere between 3 to 10 meters is very expensive. So larger companies can support these type of costs, but very often smaller companies cannot. So smaller companies will use an external test house to do pre-compliance testing for them. The goal for us is to go to the external test host with as little as possible to be tested. Really, we only want to go there once. If we have to go there more than once, it will not only incur extra costs, but a significant amount of time as well. Pre-compliance measurements, on the other hand, can be done in-house. Testing for EMI issues through the entire design process is really a positive thing. We can catch EMI problems much earlier in the design cycle and fix them before they go on to become a bigger problem later on. No one wants to fix an EMI issue when we've already got the product in final packaging. For example, we still have to go to the EMI test house. Even if we do pre-compliance scanning, we ultimately have to get our certification from the test house itself. So having said all that, pre-compliance scanning does not have to take a very long time, and it does not have to cost a lot of money. There will be further future seminars which will delve into more detail around the VMI testing and pre-compliance, and will bring to life the wider range of Tektronix product solutions, such as our MDO 4000C mixed domain oscilloscope, as shown in the slide, as well as our higher-end spectrum analyzers, such as our RSA 5000. So what do we need for pre-compliance scanning? From a pre-compliance perspective, what one wants is to replace the EMI receiver with the signal analyzer or spectrum analyzer. Now we do have to be a little bit careful here. We have to understand what the differences are between an EMI receiver and a spectrum analyzer. Specifically, do we have the right resolution bandwidths? Do we have a lot or a few trace points? Do we support dwell time? Do we support detectors? Do we support antenna factors, which are not the same as antenna gain? On the physical setup side, we also need antennas to perform these experiments. Biconical antennas are very popular. We may be able to use log periodically. We also need a tripod, and depending on the distance the antenna is from the signal analyzer, we might need a preamp in the situation as well. Now, people are often a little bit confused about this particular situation, because if you don't have an anaconical test chamber, are your measurements valid? The short answer is yes. Now, we may have to use a boardroom, or we may have to do it in a lab if the RF lab is RF quiet enough, or I even have seen customers make measurements in a parking garage. But ultimately, it is very difficult to duplicate exactly what the EMI test conditions are in the actual test house. We can make a very accurate approximation, but it is not the same. We need to understand the compromises in using the signal analyzer versus an EMI receiver, and we have to pay very close attention to as much detail as possible. We now move to the last section of today's webinar, and a brief product and solutions overview for your wireless module selections. This slide summarizes the most useful products used in wireless and IoT application testing. Cost-effective RF instruments such as the RSA 300, 500, and 600 USB real-time spectrum analyzer that we have discussed today at some length, as well as higher-end spectrum analyzers such as our RSA 5000. In addition, we have products such as our TSG 4100A vector signal generator and our MDO 4000 mixed domain oscilloscope, providing dedicated test solutions for the relative standards we've talked about, such as wireless LAN, Bluetooth, Zigbee, as well as other general analysis tools in helping the emerging protocols such as LoRa. I'd like to mention also, please keep in mind that for DC power, we also have digital multimeters, power supplies, as well as battery simulators for power management type testing. The one single user interface which enables powerful flexibility is the SignalView PC. SignalView PC has its roots from our higher-end RSA 6000 and 5000 series analyzers and is designed to run on a PC as a standalone application. But today, SignalView PC also powers our USB spectrum analyzer range, our RSA 306, 500, and 600 series. In addition, the SignalView PC also works on many of our mid-range and top-performing oscilloscopes. There are 17 signal analyses and real-time spectrum packages on our SignalView PC. And there are also paid-on options for specific protocol, regulatory, and EMI pre-compliance analyses, which we have spoke of today. In closing, this webinar has summarized the high demand of connected wireless and Internet of Things devices, resulting in the need for much more considerations when choosing a wireless module, from its device performance to connectivity standards to regulatory requirements and the ongoing need to leverage EMI pre-compliance. We hope you found this webinar helpful, and now we'll open the webinar to questions. Thank you very much.